Okay, before we jump into intermolecular forces, I'd like to start us off with a recap of what electronegativity is. So, electronegativity, we're talking about negative charge, so our electrons, and itty, that suggests that it's an ability of something. So electronegativity, it's the power of an atom to attract the electrons in a covalent bond. Now when we did this, we looked at the Pauling scale. So if we take this to be our periodic table, what we find is that across a period we are increasing our electronegativity, and when we go down a group it decreases. So our most electronegative atom is our fluorine. Now our noble gases, we don't talk about those because, key point here, in a covalent bond, our noble gases are very unreactive. They don't tend to form covalent bonds, so therefore there's no need to talk about the electronegativity of the noble gases if they're not forming covalent bonds. But our fluorine is the highest on the Pauling scale, with a value that they give of 4.0. Next we then have oxygen at 3.5, and then our nitrogen and chlorine come in at 3.0. A few key ones to note is that our hydrogen is 2.1, whereas our carbon is 2.5. So we would say that our CH bonds are non-polar, as there isn't much of a difference in their electronegativity. However, something like HCl, we've then got a difference of 2.1 to 3.0. So that's a much more different, much greater difference in their electronegativity values. So here chlorine has the larger electronegativity value, which means that our electron density is pulled towards our chlorine atom, and so we give it a delta negative compared to hydrogen's delta positive. So remember that it's the nucleus of the atoms that are attracting the electrons in the bond. So with our HCl molecules, we could have multiple molecules, and in each case the bond is going to be polar, and then we can have attraction between the delta positives and the delta negatives, and this is our dipole-dipole interactions. So it's the attraction of the delta positive on the atom of one molecule to the delta negative of the atom on a separate molecule. this is not to be confused with our hydrogen bonding. And this occurs between our fluorine, oxygen and nitrogen atoms with hydrogen. Now, it's the lone pairs of these atoms that then donate electron density towards our hydrogen. So often we use the water example. So OHH, we always make sure that our hydrogen bond is in a straight line, so that OHO must be in a straight line, and then of course the other hydrogen atoms on that water molecule. But that there is our hydrogen bond between two water molecules. So we often say that our hydrogen bond is the attraction between a lone pair on those atoms and a de-shielded hydrogen atom. So remember that the whole reason why it happens with these types of atoms is because our oxygen, nitrogen, fluorine very highly electronegative, and so they are pulling that electron density away from the hydrogen, leaving it delta positive, which then draws in that lone pair of electrons from your oxygen. One thing I also want to remind us of is, going back to our dipole-dipole interactions, is that with symmetrical molecules, our dipole-dipole cancel. So for example, BF3, if you think about each of these, so the fluorine's delta negative, your boron is then going to have effectively 3 lots of the delta plus it would have if it was just a single BF bond. But you could think about this in terms of resolution of forces in a kind of physics sense. So our electron density is being pulled in equal and opposite directions. But if we were to add all of these arrows up together, we would just return to the starting point as they all cancel each other out. And so this becomes a non-polar molecule, and so we don't get dipole-dipole forces because our dipole bonds, cancel, so no dipole-dipole forces. However, in all of these molecules, what we do have is our van der Waals. Our van der Waals forces, and this is due to the fact that in our bonds where our electrons are, they're constantly moving in random direction, and at any one moment there could be an imbalance in where those electrons are, and there you get a temporary dipole. So there it's not due to an electronegativity difference, it's due to at any one moment there are slightly more electrons in one place compared to the other, and so there you get a partial positive and a partial negative. That can then induce a temporary dipole in a nearby molecule, and then you get a temporary attraction between your delta negative and your delta positive. So the first bit is about our electrons in constant random motion. So this then causes a momentary electron density imbalance. So where we've got slightly more electrons on one side compared to the other, we then get delta negative where there are more electrons compared to delta positive where there are fewer. So this can then induce, as we now have a temporary dipole, which then induces a temporary dipole in neighbouring molecule. So this comes about because we have this molecule which has a temporary dipole. It then comes in contact with another molecule which also has electrons that are randomly moving. However, if you've got something that's slightly more negative and it comes into contact with it comes into the same area where you've got some negative particles, they're going to be repelled by that delta negative onto the other side. And so you're then left with a similar kind of setup where you've got more negatives on one side and fewer on the other, meaning this is then delta positive. So you then get attraction between that delta negative and your delta positive. So this is a momentary attraction between temporary dipoles. Now, the key thing I want us to remember here is that all molecules have van der Waals. So even if they have hydrogen bonding, even if they have dipole-dipole interactions, they all still have van der Waals. So all molecules have van der Waals. However, we can also talk about the strength of our van der Waals changing. So it is stronger as our number of electrons increases, i.e. larger atoms. And then we've also looked at in our organic molecules that larger molecules, so longer chain, hydrocarbons, because then again you've got more electrons and therefore more van der Waals. Also, we talked about branching, how that means that our molecules can't get as packed closely together and therefore they don't have the same van der Waals. So it's also determined by the ability of the molecules to get close to one another. Because remember, in order for this induced temporary dipole of a neighbouring molecule to happen, they've got to be close enough for this delta negative to cause these electrons to move over to the other side of the molecule to get a temporary dipole in that second molecule. So just to recap what we've covered. So what is electronegativity? As in the term. Which elements are most electronegative? why is the CH bond non-polar? How are hydrogen chloride molecules attracted to each other? What are dipole-dipole interactions? What is hydrogen bonding? And what elements can form hydrogen bonds? Why don't symmetrical molecules have dipole-dipole interactions? What leads to van der Waals forces between molecules or atoms? Because remember, our noble gases now will have van der Waals between those. What leads van der Waals forces to form between molecules or atoms? Here we've said what are van der Waals what are van der Waals forces? When do van der Waals forces apply? When are van der Waals forces stronger? And then the final thing I just want to remind us of is the order of these intermolecular forces. So our hydrogen bonding is stronger than our dipole interactions, and that is stronger than our van der Waals forces. And remember, stronger the intermolecular forces, means more energy needed to overcome, and therefore they're going to have higher boiling points. One last point with our hydrogen bonding is just a reminder of the number of lone pairs that our hydrogen bonding elements have available for our hydrogen bonding. So fluorine only does 1, oxygen can do 2, and nitrogen again just does 1. And so this obviously makes a difference when we're looking at HF versus H2O versus NH3 in terms of our boiling points. Our water as well, remember that our hydrogen bonds are continuously breaking and reforming as a liquid, but as a solid, they're permanent, the hydrogen bonding, and as a gas, they are completely broken. But the reason why that water has an unusually high melting and boiling point is because it's got 2 hydrogen bonds per mole of water, whereas the ammonia and hydrogen fluoride, they only have 1 hydrogen bond per molecule.